I'm going to be talking about basically graph visualization. So first, a brief introduction to what I mean by graph data. So I'm going to use the term network and graph interchangeably. I mean, computer security people tend to think of network as a specific computer network, or a graph as just any kind of plot on the screen. But I'm going to use those terms in general to mean any kind of relational data, where you have a set of entities and a set of links between them. So you have, the epitomal example is a social network. So you have a set of people and you have a set of links between them if they're friends or not. There's plenty of examples of this. Large data sets, large social networks, large computer networks, they're large biological networks, they're all over. Any field has these large graph data sets. And a lot of times, real-world data sets exhibit very complex behavior, very complex topologies. There's several terms to describe them: small world, power law, scale free. They're all used to describe the general form of how large real-world graph data sets look like. And visualization is very key to understanding these kind of data sets, because if you're just given a list of A is friends with B, B is friends with C, C is friends with D, and so forth, in textual form, you're not going to have any idea or any chance of comprehending what that means. So visualization is very important in terms of actually understanding the actual structure of the network or the actual connectivity and topology of that network. So in general, for visualization of this kind of abstract data, there's a general mantra in terms of how to approach this kind of a problem. And that's proposed by Schneiderman decades ago in terms of a top-down approach, where you start with an overview. Then you figure out where in that overview you want to look at and zoom into that and filter out everything that's not relevant to what you want to look at, and then query details on demand in that specific subrange of the data that you want to look at. That's a very common paradigm for visualizing large data sets. But the real question is, why is this important? Why do we actually want to do this? Why don't we just visualize all the data at once? And that's really because there's a fundamental limit to the amount of data that can be presented to the user at any time. There's a finite number of pixels on any given display system. The eye has a limited resolution about what it can see, and even the brain has a limited resolution about how much it can process at a time. Specifically with respect to color, you can only really perceive about 7 to 10 colors or so before you start getting overwhelmed by discrete colors. Analog colors are a little bit better, but discrete colors is very interesting perceptual limit in terms of the psychology of how the human perceives that. So a lot of times, in order to generate this overview, in order to do this InfoVis approach, you have to use simplification or summarization to reduce the data into some digestible amount. So we have to, in general, reduce the amount of data that we're looking at to whatever is a digestible amount for the human brain to process. But this actually limits what we can do as far as generating such an overview, right? Because this is a fundamental limit of the perceptual system of the human eye, human brain. So as the data increases further and further, this perceptual limit really reduces or really restricts how much of the data we can show. Because if there's a finite amount of data we can transmit at any given time to the user as an overview, as the data increases, this fixed limit stays the same, so we're showing less and less and less of the data as the data keeps growing. This is particularly a problem for graphs and graph data sets because of what I mentioned before. A lot of real networks have this scale-free property, a self-similarity problem. Mathematically, this is defined as there's a degree distribution that follows a power law. That is, there's very few nodes that have a very high degree, and then that falls off very quickly into a long tail of a lot of nodes that have very low degree. That's how it's mathematically defined, but in practice what it means is that these scale-free networks exhibit a very similar behavior regardless of what scale you're viewing at them at. If you view a small subset of the data, it will generally look very, very similar to if you took a wide-angle view of the entire data set. You'll see there's very few high-degree nodes and very few large clusters, then a lot of very, very small nodes or very, very small clusters, regardless of what view you're looking at it. And the consequence of this is that most overviews of large graph data sets will look very, very similar. And so you won't be able to tell much about the graph other than, hey, it looks like a power law network, or it's a social network-like data structure, or you can maybe tell how many clusters there are, but you won't be able to tell very much about the data set. You won't be guided to any interesting features of the data set. And so this has led to the development of kind of an anti-mantra to Ben Schneiderman's InfoVis Mantra. And that is, rather than starting at the top and looking at an overview and trying to drill down into what's interesting, let's start with what's interesting and then look at the context around that to see why it's interesting. So we search for what's interesting, whatever that means, whether we have domain knowledge or whether there's some data mining metric that can tell us what's interesting, and then we show context around that. So we can show, okay, here's a node that's important. Why is it important? And then we can expand around to see more of the general picture of what is relevant to this important feature of the data set. But that leads to an interesting question in that, how do we find that interesting starting point? There's some necessary information needed in order to start from the bottom. We need to know what is interesting to start from, and we need to have an indication of, or some idea of, which direction to explore the data set, right? If we explore at random continuously, we'll just get a big tangled mess again, like we had in the original overview. But if we have a focused direction saying, okay, here's A, here's B, there's some connection in here, maybe we want to explore that further. If we can indicate that to the user, we can guide the exploration process. And that's really the motivation behind the whole idea of a visual recommendation system. So we want to recommend to the user not just the initial starting point, or if they have a search idea, they want to say, the epitomal example of a recommendation system in general is a search engine, right? They enter a search term, and the search engine returns, hey, here's a list of results that might be relevant to that search term, sorted by what's most relevant to what you're interested in. For a visual recommendation system, we want to go a step further than that. We want to not only show an initial list of what's interesting, but as the user explores this further, we want to modify that focal point and recommend additional directions for expansion. So we want to say, okay, if you're interested in this direction, we'll throw away the other directions and focus more on what's relevant to what you're looking for. And so this can help an interactive visualization of this kind of this large graph data set in terms of what we can recommend to the user as far as their current viewpoint, and help aid this explorative process to be able to find, what is the user actually interested in finding out about the data. So here's an example of a visual recommendation system that we've implemented. Starting from one initial point, so one initial node in the graph, the system recommends a small subset of nodes. The user can select one of those. It adds that to this overall chain of nodes and selects a new set of recommendations. And then the user repeats this process, selects another node, it adds that to this chain, and selects a new set of representations. And this has been repeated 3 times, so we have 4 selections shown here, right? One initial viewpoint selected by an initial recommendation, and then 3 points of expansion where the user is focused in a particular direction in this system. And then the system is showing the connections between these nodes, including some potentially hidden recommendations. So this view is this recommendation system is based on several underlying recommendation metrics based on this graph data set, because we can't just choose nodes at random. That wouldn't be very helpful. So we look at how important the nodes are with respect to the network, how important the nodes are with respect to the current view of the network, and what previous users have explored in the data set. Because if there's an important chain of events or an important chain in this data structure or in this graph, it would be nice to recommend that to future users. So a little bit about importance. Network centrality is a long-studied metric for large graphs, and as far as how to determine how important every node is to the structure or topology of the network. There's lots of different metrics for this: betweenness centrality, eigencentrality, Markov centrality, Any one of those can apply. It's just a matter of balance of quality of the importance metric versus the computation time. Eigen tends to be a good balance between both. That's basically what Google uses to do their search results. Relative importance is a little more complicated because we want to say, given a certain view of the network, how important is a node with respect to that particular view? And so we want to say, like, with respect to a given node, if this node were suddenly to disappear from the network, how would that affect another node in the network? If node A was to completely disappear, would node B's importance increase, decrease, stay the same, or it's very volatile or some nodes are very volatile how they affect each other, and so we want to measure how that affects the network, and we can compute this very simply, essentially by doing exactly that. We can take this large network, remove a node, compute the centralities again, and see how much they've changed, and do this for every node in the network and determine basically an entire matrix of relative importance. So how relevant is one node to another node's importance? And this is actually very interesting in terms that it can reveal relationships between unconnected nodes even. So you can see this node and this node are very relevant to each other, even if there's not a direct connection between them. And that can be very important in certain applications. The other importance metric we look at is user histories. So this is based on item-to-item collaborative filtering, which is basically the same thing that has been well studied, well used in a lot of commercial applications. Specifically, Amazon's recommendation system uses this. They look at people who viewed this or purchased this item also purchased or viewed X, Y, and Z. And that's essentially what we can use here is we can look at people who have, or users who have viewed node A, B, and C have also viewed nodes D, C, or D, E, and F, and use that to influence the selection process. So this kind of adaptively learns users' behaviors or specific users' behaviors or multiple users' behaviors, either way, depending on if you're in a collaborative environment or not. And this can be weighted into this recommendation system. So overall, like I said, we have this is just for a static network, and as the user selects nodes, the focus changes. The history of the interaction is shown in that arc up to the left, and new recommendations are added around each new selection down to the right. Excuse me. But there's an interesting issue with this because sometimes there's nodes that might not ever be shown to the user, or there's nodes that will always be shown to the user regardless of how important they are. So we did a certain amount of evaluation study to see, with this recommendation system, how does the system recommend the nodes with respect to how important they actually are. So on the y-axis here we have the concrete importance according to the centrality metric, and on the x-axis we show how often the recommendation system presented those nodes to the user, or how often the nodes were selected by the user. And so we can then use this kind of an approach to look for outliers, which is another interesting way for an analyst, for example, to look for a good starting point. We can say, okay, here's a region of the network that's been unexplored by anybody else so far. Why? And we can look at a particular feature of the network that the recommendation system has failed to show to the users. Or we can look at, here's a section of the network that has been overexposed to users. Once again, why? And the analyst can start at that point and look at the details of why that particular region has been overexposed to users. And so that's one of the ways that this kind of a visual recommendation system can aid analysts in analyzing a static network. So this is kind of the halfway point in the graph. I've talked about static graphs so far, but what about dynamic or streaming graphs? Because these networks are very rarely one snapshot that stays the same for all time. A social network, people make new friends all the time or delete friends off their social network, or if you want to look at it at a finer resolution, people are communicating with a subgroup of people, and then they're communicating with a different subgroup of people of their friend list. So this dynamic social network is constantly in flux. And so we wanted to look at how do we analyze these dynamic graphs, because they're all changing and evolving over time. And thus, the recommendations for what the user should look at will also evolve and change over time. Animation is commonly used to represent time, but that's not necessarily helpful because, in most cases, because A, the animation requires a stability of the visual representation, and B, there's a necessity for animation doesn't very well facilitate static analysis of long time periods, because you have to sit there and watch the animation for 5 minutes, and you don't really gain that much unless you're jumping back and forth and looking through the animation. It's really not as helpful as a static visualization of the time can be. So just a quick definition for dynamic graphs, we're talking about graphs that change over time, and we can look at, in this case, we're looking at not streaming graphs, but specific time points. So we're looking at time A, the graph is this, at time B, the graph is this, at time C, the graph is this, and we're looking at how the graph changes between those time steps.
Is there any notion of like prior information or pre-existing biases that might affect the initialization of the graph?
Of the graph data itself?
So you might know, let's say ahead of time, that certain clusters or certain nodes are more or less explored than other nodes?
In this particular application, we haven't explored that yet. In the previous application I showed, that was that last image that I showed, was looking at over or under exposure because of that. The same idea could be applied to the dynamic graphs, but we haven't done that yet. In any case, one interesting idea to look at this that has been proposed, originally kind of inspired by Randall Munroe of XKCD, was to look at a storyline of the evolution of this network. So these storylines are looking at basically evolving clusters. So we have a group of people, each line is an entity, which would be a node in the graph, for example. And then the bundles of lines indicate nodes that are grouped together, either because, in this case, because they appeared on scene or in the same page or whatever of the novel or the movie, or in a graph because they appear in the same cluster as each other, and looking at how these nodes move between clusters over time. So we wanted to take this approach and look at how we could apply this to dynamic data sets automatically, rather than just a hand-drawn, custom-tailored visual representation of a story. So it's a nice summary of time-varying behaviors, but there's also an issue that this doesn't necessarily scale very well to large data sets, right? We already have an issue with large graphs exceeding the number of pixels we have available to us. If we try to look at such a large graph over time, we can exceed both the one dimension of looking at how many nodes we have and the number of time steps we have. So it can very, very easily exceed even the number of pixels available to a giant power wall, for example. But given a focal point, an ego, if you will, storylines within such a large data set can provide a good temporal context of how that one entity has moved throughout the network. And so for that, we've developed this approach called Egocentric Storylines. So we're tracking basically one user, in this case shown at the bottom, how its closest members or most relevant neighbors have changed throughout a data set using the storyline approach. So there's a brief overview, or complicated overview, if you will, of the whole egocentric storyline system, because it's a very dynamic, very streaming system, trying to handle a large amount of data at a time. And so it handles really one time step at a time, and it tries to cluster it, filter it, lay out those storylines based on previous time steps and the current time step, and then render it such that the user can actually be able to see what they want to see of the data set. And so I'm going to try to quickly go through this. Data management, basically like I just said, we're looking at one time step at a time, using a SQL database to be able to just store it all and be able to get the data that we need at any time step. Implications of this, because we're working on only one time step at a time, we're limited in the amount of calculations we can do. We can't necessarily compute a global optimization. We just want to get a kind of a greedy approach to get how good can we do fairly quickly looking through this large data set. The clustering, likewise, is a streaming operation. So we have the previous time steps clustering, and we can cluster a current time step, and then align those two clusterings together. So we can say, okay, cluster A in time step 3 matches to cluster 7 in time step 4, and we can look at how to align those two and say, okay, that's the same cluster persisting over time. And so we have this alignment step that basically helps sort this graph into a more stable network or more stable set of lines. The math is in the original paper. I'm not going to go over it too much because that's a fairly common modularity clustering algorithm. But we use a Jacquard index to do this association, to basically say, okay, if there's no intersection, obviously they're not connected. If there's a 90% intersection, they're most likely going to be connected. And that's basically what the Jacquard index measures. And we have a fairly efficient measurement, or a fairly efficient algorithm to compute that. Once we have this, we also want to be able to say, okay, within this large network of clusters of this large graph, what is the user actually interested in looking at? And so from here, we wanted to do basically that same static graph recommendation system that we showed in the previous implementation, but for a dynamic graph at each time step. So we want to consider both the overall relevancy, a temporal relevancy, right? If it was relevant in the previous time step, maybe it's still relevant even if it's not actively relevant in the current time step. We want to preserve some amount of stability from that. And we also want to preserve an interaction relevancy, right? As the user explores the network, we don't want to discard entirely the previous exploration. We want to have some amount of persistence as the user explores different egos in this large network. So the relative importance can be computed using a centrality or a relative centrality metric or a cosine similarity metric, as in the previous static example. The centrality sensitivity can be very computationally expensive, but it can be very helpful. Alternately, we can just use a very simple distance-based metric. So we can look at geodesics in this graph and look at the shortest path and say, okay, given this node, what are the nodes that are 1 away, 2 away, 3 away, and just look at that because we're looking at one node at a time. That's a very simple relevance metric, but it's very efficient to compute for large data sets, particularly if in a real-time situation. We also want to preserve, like I said, the temporal relevance. So if a node's importance is changing over time, we don't want to throw it away immediately if it becomes unimportant for one time step. We want to just kind of shift its importance a little bit. So we can add a time window to this idea. So we can say, okay, the most recent time step is very important, but as time fades, for X number of time steps, the importance kind of fades away as well. And so this is a very simple way to preserve some kind of temporal stability in this relevance metric while still streaming through the data. And lastly, we want to do an interaction relevance, where we want to reuse the previous selections in importance values without discarding them entirely. And so we can import them basically looking at the previous time step of importance and add that as another weighted value into the overall importance. And so we can combine these into one overall importance for every node in the graph and look at, okay, we want to select the 20, 30, 40, whatever the user wants, most relevant nodes in the graph according to all of these different relevance metrics. And we can use that to say, okay, we only want to look at 20, 30, 40, whatever the user wants lines relevant to one ego that we're focused on in the network. For the layout, we don't want the interaction to affect it, so we want to keep the weight used for the layout algorithm to be just on the relative importance and the temporal importance. Filtering, basically, like I said, we want to cut down the number of nodes that we're showing. So like I said, maybe only top 20 or 30 nodes that the user wants to see. Skip that really quick. The storyline layout is an interesting approach because the original storyline algorithm didn't have a very good layout. We had another paper that looked at how to compute a good storyline layout, but it used a genetic algorithm that was exceedingly slow. Computed a great layout, but it was not practical for any dynamic approaches. So here we take a greedy approach to this problem, particularly because we're looking at streaming data in this sense. We're only looking one time step at a time, and we want to realign, given one time step previous, how can we best fit the new time step to this existing data set? So where do we add the new clusters and nodes? Where do we insert them, et cetera? So we have this relevance heuristic that we've pre-computed. We have clusters that we want to sort into these layers, and we also have the individual nodes within the layers that we want to sort. And in both cases, we want to preserve stability as best we can. We want to keep the lines as straight as possible in these storylines, because otherwise it becomes illegible. And so we use this to do a greedy sorting, a greedy algorithm, which is approximate to what is ideal, but it's not necessarily rigorously enforced. So a quick example, if we have 2 clusters in the previous time step and we have 3 clusters in the current time step, we want to try to take the clusters that align and match them up with the previous time step, adjusting the sizes of these layers accordingly. We want to insert a new layer for any new clusters that have appeared. And then within those clusters, we want to start mapping nodes. So any node that persists in that cluster from the previous time step, we want to assign to that cluster, or to that specific position to keep it straight. And then insert new nodes as necessary in the available spaces. And in this manner, we can then create a set of storylines in a streaming manner over a large range of time, looking at only one time step at a time. So this heuristic is fairly efficient, fairly quick, but it's not necessarily perfect in terms of layout quality. In theory, if you had a global optimization, you could create a better layout. But the approximate ordering provides a good amount of stability for a specific egocentric view. And lastly, the interaction. We have a system that has to provide an initial recommendation. So there's an initial selection process based on the importance of nodes, generally, or domain knowledge. And then there's the explorative process. Any one of these lines can be selected to be the new egocentric node and brought to the bottom of the plot and say, okay, this is our new focus, reorganize the nodes and recalculate the layout according to this new ego that we've selected. A couple quick examples. Here's one where the egocentric node at the bottom switched clusters a couple times. However, some of the persisting other highly relevant neighbors still persisted over time, even as it shifted clusters. For example, at this time step, it shifted from one cluster to a different colored cluster, but a lot of its, or several of its neighbors persisted over time. Here's a slightly larger example where a cluster or a node shifted back and forth between clusters, but also maintained a close relationship with another fairly large cluster for most of the time range. So I've shown you I've shown you an approach to looking at dynamic graphs in an egocentric way, starting from a bottom-up approach. There's still a lot more that we want to do and can do looking at this kind of an approach. And the applicability is not only to statically connected networks, but because this approach is very streaming oriented, it's also very relevant to a real-time network, for example. It would be interesting to try to apply this to real-time computer security network or social network or tweet network or any other kind of real-time network. And we want to monitor one entity over time and see how it's moving through or how its neighbors are behaving over time. And with that, I'm going to open the floor up to questions.
I lost track of why you only have 3 relevance measures in doing this, but I'm curious about how do you apply these ideas to higher dimensional spaces if you have additional measures of relevance, for example?
Right now, we're just using a linear combination of the 3 metrics, but that particular function could be arbitrary. If you had a higher dimensional input metric and you wanted to apply a more complicated function to that, even a machine learning approach to that, a neural network could be used for that, as long as it outputs one final value saying the relevance is 0 relevant or 100% relevant, or it's kind of flexible in that way. Right now we're just using, like I said though, a linear combination of the different metrics that we've come up with.
Is there any way that this could be used to, say, optimize a swim lane process? I mean, oh, I'm sorry. So is there any way that this could be used to optimize a swim lane process?
Sure. I mean, I think I'm following you in that the layout algorithm is streaming. It is a greedy approach, but it's heuristic based. So if you have some heuristic that could say this is a good layout versus a bad layout, and it would potentially help that, yes.
Or if you were like dynamically reallocating resources?
Yes, actually. Such an approach could potentially help with that. Also just help with monitoring that. We actually have a recent paper submission that I didn't show here, but looking at an analog equivalent of this, looking at resource allocation in, one of the examples was a cloud computer system. Right? So you have different processes in this cloud computer system with different behaviors, and maybe one computer is reallocated to a different process, so its behavior changes. And so you can see, okay, here's 2 behaviors, and one node shifts between the different behaviors. And so we're looking into that kind of analysis as well, which I think would be more relevant to what you're asking.
We got question.
Sure.
I have a question. Well, so you're looking at dynamicity in terms of how nodes are connected to each other.
Mm-hmm.
But what about types of connections, types of relations between the nodes? Are you looking at that? So if it changes between person used to be a friend, no more friend,
Mm-hmm.
but I don't want to see messages from that person, something like that.
Right. We have projects looking at that for static networks so far, and such approaches could be very transferable to such a dynamic approach. Because we have like a sociological network, and we're looking at friends versus bullies, for example, in a school network. And such things could easily be extended into a dynamic space because the similarity metric we're looking at is very flexible. Once again, right now we're just using a linear combination of weights, but you could easily add, okay, this connection is a friend, we'll maybe make that positive y-axis. This person's an enemy, we'll make it a negative y-axis, and see how many nodes flip entirely. That's a simple extension that would help in that kind of a situation or that kind of data analysis.
So we can go to the break.
Mm-hmm.
Thank you, Chris, so much. And feel free also, if you think about a question afterwards, use our forum to post the questions on the Meetup website.
Yeah.
And,
Or email me directly or
exactly.
approach me during the break or whenever.
Great. Thank you so much.
Yeah, thank you.
We have 15-minute break. We have